Okay, what's up and welcome back to the channel. This is the Prokon Geek, and in today's video we're going to be looking at Let's Design a Double Story Building Together Part 5, where we're going to be looking at the takedowns for preliminary sizing of our bases. So without wasting too much time, let's get right into the video. Okay, so first things first, if this is your first time coming to the channel, please click the subscribe button. Also remember to like and share the video with any of your colleagues on the platform or on Twitter or any of your social media. And once you have done that, it's time for us to get started. So as I told you, and we already have done part 1, part 2, part 3, part 4. And if you remember the first thing what we did, I always like to repeat this, we took our architecturals, we cleaned the architecturals, we established our structural layouts, and later on we did the tributary layouts. Now, and then we also managed to establish our grid lines and do the tributary layouts, which is great. Now what we need to do is, normally as I told you, the design, what you do is you get your calculations, you preliminary size the foundation that you would want to use, or you just see the amount of load that will be going down to your foundation, so whether you can see if the pad footing that you just decided to use will be okay, or in a case you may need to use wrapped footing, or you may want to use piles. All that is determined when you do the preliminary sizing. Now normally when you're designing, the best thing to do is to do it from the top going to the bottom, which is what we're going to do previously, as opposed to what we did in the previous series where we did a bottom to top design, where we had actually done the calculations and then we started designing this going up. But right now what we're just doing is we're still doing the same method where we go from the top going down, where we're just looking at the loads that are going to the foundation. But this is important, as I've told you, for actually determining if the foundation that we need to use, or the one that we have chosen, is going to be of good use. Okay, having said that, so the first thing that you do now is we're doing our takedowns. Remember, the Excel sheet is available. I already have another Excel sheet that I've already shared with you guys. Please, there's a link in the previous video where I did the takedowns, where you can get the Excel files. But at the same time, because I'm going to be using the same Excel, but that is going to be tailored for this particular building, I'm going to leave the Excel file in the description below for this video, so you can always download it if you want. Having said that, so there we are. We established our tributary layouts, and as I told you, the first floor is very similar to the ground floor and the roof for this building, but in essence we're just going to be using the loads that are coming from the roof, right, where you can see my mouse, and then the loads coming in from the first floor. But the loads coming in from the ground floor do not really have an impact on our foundations, that is to say the pad foundations, because we're doing a frame structure. As these, that is to say, if we go to the foundation layout, you can see there's going to be a strip footing, so the slab that is going to be within the building for the ground floor will be bearing directly onto the ground, and the other loads will be transmitted via the walls straight into the strip footing. But what we are mostly concerned about are the loads that are going to be coming in from our columns and going to our pad footings or our pad designs, which is what we want to see today. So we need to find out if the pad footing will be okay, and also what size we may need for that pad footing. And to do that, that is why we need to do the takedown. So the first thing that we're going to do is we need to do a takedown for column C1, which is this one. Then we're going to do for C2, and then we're going to vote for C3. So what we're going to do is, as I told you, I already have this sheet. I'm going to leave it in the description below. But one thing that I'm not, let me just tell you beforehand, those links that you see right now will not be in the Excel that I've given you. The reason why is because under law, yes, I know this is me, a guy giving tutorials on YouTube who was using a Prokon back in the day. You know what? I know. I'm not trying to take the high moral ground here, but all I'm saying is, at this point in time, it's not good for me to be giving you or distributing these Excel sheets or PDFs. Anyways, I'm not saying I'm not going to do it, but for me to distribute the Excel with these PDFs is not the best thing for me to be doing, especially when I am doing it via YouTube and giving links to the public. Under my knowledge, it's not something that is, I'm just saying this is not the way. But all I'm saying is you could definitely get these PDFs from somewhere, and if you are quick, you understand what I'm saying. Anyways, what I'm going to do is the Excel, the bulk of the Excel is going to be there because I created this Excel, and also if you want, one thing you're going to notice for the roof, the minimum loads to be used are already going to be embedded in the Excel, so you don't have to worry about it. But now to get started, what we're saying is we need to calculate the loads that are going down to C1 for this particular building. So for this particular building, the first thing that we need to start off is we need to start off at the roof. So at the roof, the first thing that you do is, first up, we have to take into account the roof loads. So for the roof, you obviously start with the dead load before you go to the live load. So one thing that you do is you enter the dimensions of the tributary area from AutoCAD, or just straight away you enter the area. So in this case, by default is 1. We need to change it to the area that we have, and the roof pitch by default is 5 degrees because that's the minimum when you have IBR sheets, that is to say metal sheeting, which is what we're going to have in this case. So some of you may argue, aren't you supposed to measure the angle from the architect? What you can do is you can go there and then you can snap to this point, but as you can see, the angle is 1 degree, but the manufacturer of IB sheets or IBR sheets where I'm from, that is to be particular in Zim, it needs to be a minimum of 5 degrees. So that is what we're going to use. So in this case, you're going to put whatever pitch is there for your drawing, but in this case, we're going to use 5. So it's going to automatically calculate the reduction factor for you. So that's one thing that's already going to be covered for you. You don't have to worry about that. The next thing that you're going to do after that is you need to enter the area of the tributary. So go back to AutoCAD, and what you're going to do for this point, one thing you need to notice is the reason why I have this area and then I also have this area is because this area is encompassing of the canopy at the front. That is the slab that is going to be at the front. If you go to the architecturals, this is this part of the canopy. So but when it comes to the roof, this is not included. This area is not going to be contributing anything because there is no roof at that point, but the roof actually starts from the inner wall. So for your case, what you need to do is you need to come back. That is the reason why I decided to have 2 areas for this portion. So this portion is going to represent the area that is directly coming from the roof alone and not part of the canopy slab. So if you go to that, the area you're going to find it's 6.148 blah blah, because it's 6.148 zeros. What you're going to do is you're going to divide that by 1,000,000, and when you divide it by 1,000,000, what it means is 6.15. So go back to this and you're just going to key in 6.15. Now that you've keyed in 6.15, what is the factor that you're going to use? So remember, this can be coming from the ASCE 2002, but you will find that this is adopted from the Residential Design Guide 2017. This is also coming based on the ACE, but obviously now from 2017. So you can disregard this, and what you're going to do is you could say ACE 2017, but you could also say the Residential Design Guide 2017. Then what are we going to do? So the roof from the architect, I consulted with them way before when they gave me this drawing. So this roof is supposed to be IBR sheets. We're saying metal roofing. This is galvanized. You could say it's galvanized steel, whatever it is. So in this case, if it's metal or IBR, we see that the load is 14 pounds per square foot, or in kilonewtons is 0.67 kilonewtons per square meter. This is the minimum. Remember, this is the minimum. So I could enter, or I could key in 0.67 right there, or I could key in 0.75, I could key in 0.7, because the minimum is 0.67. It was supposed to justify the minimum. In this case also, normally you want to play around with the minimum because that's the average that has been seen in the field. In this case, I decided to play with 1 to cater for any contingencies that could go for the, you never know, in the manufacturer, or the deviance that could happen whenever they're producing these IBR sheets. Once that is done, we've keyed in 1. The next thing that you would want to do is to calculate for the live load. So for the live load, what you're going to basically do is to provide the live load vector for the type of roof and state the code. So in our case, the vector is going to 1. You can always open up the code that you're going to use. And this particular one, we have the imposed roof loads for roof, and if you want, if you go to, it's actually section 1 clause 4, it has the minimum imposed roof loads. So if you want to go, let's just check, let's just go down. So this is section 1, and we want to go to clause 4 where you have the minimum imposed roof loads, and in our case we have an inaccessible roof. So you have the minimum imposed roof load, or the minimum imposed load on a roof with no access. Where no access, they're trying to say you only access it for cleaning and maintenance. So you either have uniformly distributed snow load that you have to calculate, or you use the redistributed snow load, or use a uniformly distributed load of 0.6 kilonewtons per square meter measured on plan for roof slopes of 30 degrees or less, or a uniformly distributed load of 0.6 multiplied by 60, subtract the angle which is above 30 divided by 30, and that gives you the load. Or if it's going to be greater than 60 degrees, the pitch, that means you're going to use zero load as stipulated there. So in other words, as the pitch increases, the load on your roof actually increases as well on plan. So in essence, we are saying the higher the slope on the roof, the less the load. But in our case, we are seeing that the minimum that we can use is 0.6. So as I said again, the 1 is just to cater for any contingencies that could come up. And the reason why we're doing this is because if you go and type 0.67 there, this is 4. And if you type 1, this is 2. We just add in a few kilonewtons. 2. It's not that significant. It's not significant, but it's good. It just helps to cater for any deviance that happens as things are being produced, or if the load increases. But in our case, you're in Zimbabwe, you're in Africa, you're not expecting any snow, so you're definitely you don't have a need to calculate the snow loads, so you just have to enter 0.6, but in our case, I'm just going to put in 1. Now once we're done with the roof, the next thing that we need to do is go to the slab. So the slab obviously has the dead load and the live load. So for the dead load, we have the slab thickness and the screed thickness. So normally what people use is they want to use the load for the floorings and everything, but I just want to approximate everything to screed. So in this case, the screed usually use the standard of 50 millimeters. Normally it's 30, 40 or 50, but I go 50. And for the slab thickness, remember we sized our slab and we agreed we're going to make it I think the size slab we did is somewhere, yeah, this is where we sized everything, 220 and 170. So the 220 slabs, you're just going to key in 0.220, and the area now is the area for the tributary. So in our case, the canopy thickness is different from the actual first flow thickness. You understand? That is very different. It's very different. So that is why in this case, and remember, when it comes to C1, you're definitely going to have to put 2 slabs. So you have the area that is just covering for, if you just remember what we did, we have this one, this is going to be the 220, and then we have a different area there. So what you would normally do if you want is you could calculate them in 2 portions. So you just have that one coming up, and then what you do is you hatch, you select that comes off. Once you hatch this is okay, then you put it inside 32, and then you give it up to 50, make it 50, and then change the color to anything that you would want. So this is what you would do if you want. You would select this, get the area, calculate the loads for this specifically, and then you could also get this point and then calculate the load specifically for it. But what I'm going to do for this particular one, I'm just going to use this area. Then I'm also going to then calculate what percentage this is 3.97. We could say 3.98 divided by 6.15. What I'm going to do, calculator, this is going to be 6.15 divided by 3.98. That gives us a 1.5. So in essence, we have 1.5 slabs. So what we're going to do is we're going to take this entire area for this one in particular, and then we're just going to use this to calculate our load. So this is what's going to happen. We have 10.1. This is 10.2. So this is what you're going to do for the load. The area you're going to put in 10.2. This is preliminary. Remember, this is why we're doing this. And if you want to verify the weight of the concrete, just go to the weights of building materials. This is just for the BS. You can know the BS that you need to check. And then also this is the BS for reinforced concrete to see how those things deviate and how you can use them. So in our case, we're going to say we have a slab thickness of 0.22 and screed thickness of 0.051. But since we said for the slabs, how many slabs? Normally we were going to have 1 because of the first floor only, but in our case we're going to put 1.5 because of what we just calculated. You saw me do the calculation. This is just for preliminary, but if you have time and you want to input it, the best thing is to calculate the load for the slab for the 0.22 section on its own, and then you do for the 0.170 section on its own with its screed or without screed, depending on what you would want. But for this particular one, we're just going to calculate for the 0.22 section, and then we're just going to say we have 1.5 slabs. Why? Because we do have the portion of the canopy that's going to be up on the eaves level, which is not available on the which is on the eaves level, but at the eaves level we don't have the 0.22 thick portion of the slab. Once that's done, the next thing that you need to do is go to the live load, and once you're at the live load, now the most important thing is to choose your vector. So in this case, since we're using BS, particularly lot, remember what you need to do is also you need to go back to the architecturals and you need to identify what the area is going to be used for. So in this particular, we have office and we have storage. So in particular, we're going to have storage for office spaces. So where you go is, let's just check. This is where you have the loads for your building spaces. So you're not going to use residential because that is section A. What you need to do is start looking at section B and C. Why? Because B is offices and work areas, right? And then once you're going to do is you have this. These are the loads that you can use. And remember, this is workrooms, light industrial without storage. So without storage, you're going to use 2.5. But now because we need storage, we need to look at a place where we have storage. So in cases where we have storage, we now need to start looking at reading rooms with no books area. That's 2.0. So that's not what we're going to use. But in particular, from my experience, what we're going to need to use is we need to find somewhere where there is storage of materials. So that usually comes to section E. So what you need to look, this is the general storage of anything else that is not specified is 2.4 for each meter of storage height. But generally, if you're going to have cold storage or anything, the minimum that you usually use is 5. This is where you have 5 rooms, filing and storage space for offices is a 5. So you definitely, and if you want, we can always check with SANS as well. So with SANS, it's more specific than BS. If you go to SANS, what it then says is, if you go down, let me just page down. Where is page down? We're just going to go with page down. So we need to look for section, I think it's section, let me just right, this is section D. Nope. This is, yeah, there we go. Filing and office storage areas, stack areas in libraries and archives or anyway, 2.5 meters per stack of height, but it always has to be greater than or equal to 5.0. So that is where you need to institute your load. So this is the load that you're going to use. So in essence, what we're going to do is we're going to go back to Excel, and once we're back in Excel, you're going to have to put in 5. And you normally, one thing that you would want to know if you're doing it correctly, your dead load usually is bigger than your live load. So that's one thing that you need to just look at when you're designing your buildings. Now this is done. The next thing we need to look at load bearing walls or slabs. So fortunately for us, if you go back to AutoCAD, we don't have any load bearing walls on our slabs at either the first floor or even at the eaves level. So we're good to go. Now we go back. The next thing we need to look at are the beams. So in our case, we have different beams of different lengths. So we have a 690, then we also have a 300. No, we have a 600. When it comes to the eaves, we have 600 and 300. Then we have 690 and 450 if you look at it correctly. So what we need to do is, let me go back. What I'm trying to show you is, if you look, we have 690 and 450, and then we have 600 and 300. So you go back to Excel. What you're going to do is, let me put 600 there. Then what you do is you add this up. We're just going to add this up because it's a preliminary design. Then we're just going to say this is equal to this divided by the count. So we're going to say count, and then we're going to count from everything there. Yes, that is what I want to do. So you get 487.5. Are you sure that is correct? What I'm going to do is, let me just do this the old manual way. It is still 4, definitely. So this is the beam depth that we're going to use, which is 487. So that's 487.5. Now for the width, remember we have 300 and 230 dip beams. So in this case, it's going to be equal to 230 plus 300. Then if you want, then not if you want, if you proceed, you're going to have to divide that by 2. All right, so this is the type of beam that we're going to use. Oh, remember, it's supposed to be 0.487 not. That is correct. And this is going to be point, and then this point, and that looks great. Okay, this is what you're supposed to do. And then the next thing that you're going to do now is to measure the length of the beams, so, and the width of the beams. So in this case, let me see what the tributary areas. We have 2535 and 2070 because we're looking at one column at the moment. So that's 2.535 and 2.070. If you go back to AutoCAD, that is looking nice. And then you have the total length, and then automatically what it does is it calculates the load for you. And then what you're going to do is you're going to need to go to where it says beams, and in this case you have 2 beams, which is okay. That is why we're averaging everything out. Now after you do, you need to load bearing walls on beams. So in particular, for this particular one, remember you do have walls on the eaves, and then you do have walls on the first floor as well. So what you're going to do, I know in this case at the first floor, when it comes to the front, you're going to have glass, but we're just going to approximate it wall for now. So what you do is you need to measure the height of the wall. In this case, it's going to be 4.725. Why am I saying this? Because remember, in one of the videos, we measured the height of the eaves walls, the parapet walls, which is 725, and then the walls of the height of the walls on the first floor is 4 meters. So we're going to use 4.725. Now the next thing that we just need to use is the length of the walls, but the length of the walls, because they're sitting on these beams, is going to be equal to the length of from the beams, which is in this case was calculated to 4.605. That's okay, and this is the total load that you get. Now once that is done, the next thing that you're going to do is you need to look for your column. So in this case, what is the section depth? So for columns, remember we use a column of 500 by 230, so it's going to be 0.5 and by 230, which is okay. Now what is the height of the individual column? Is 4. Why? Because if you go to AutoCAD, if you check, our column is going to be spanning from there to the first floor. So from the wall plate to the first floor, and from the first floor down going to the bottom. So we're just going to use 4. Even if some of the 4 meters will be support, we're just going to use 4 for now. So that looks fine for me. And remember, we have 2 parts of our column, so we are good to go. So we have one roof, 1.5 slabs. Then we have, okay, we can just say 1, but we don't have any walls or slabs. Beams, we have 2. Walls on beams, we have 1 because we already used 4.725 instead of just 4. And then for the columns, we have 2. Now the last part we need to use for the slab, the stub column. And in this case, section depth, the section depth is still the same. But for the height of the column, what we need to understand is, what needs to happen is the base. This is the recommendation from the Geo Survey, and the guy who already designed this before, they told me the top of the base has to be 1000 from the natural ground, but then the natural ground level is 300 from the DPC level, that is the substructure. So anything beneath the substructure is going to be the stub of your column all the way to the base. So that is why we call it the stub column. So in this case, the stub column is going to be 1000 plus the 300 from the natural ground level to the DPC, because beyond the DPC, that's the substructure, and beneath the DPC, that's your, beyond the DPC, that's the superstructure, and beneath the DPC, that's the substructure. So once that is done, the next thing that you're going to do is you're going to key in 1.3, so that's 1.3 meters. And once that is done, you have 3.59. The next thing that you're going to go is you need to go to your results, and your results will be keyed in automatically for you, where you have the dead loads, and then you have your live loads there in that column, and then you have the total affected loads, and then you have 82.67, and then you have the total unaffected load. And then if you want to calculate the ultimate limit, you can always use BS or SANS. This will just use whatever you want. Then BS, you're good to go. Once that is done, the next thing that you're going to see is for your sizing of the columns. No, for the pad footing, you're going to be using the serviceability limit. So that is the unaffected loads. And in a case, the minimum that you can use for any soil that is not expensive. So if it's not going to be on expensive soil, but mostly for most soils, the minimum is 200. That is the minimum pressure that they can allow. Normally, you might find anything in the 150 or anything, but that's too. So from the geotechnical as well, I'm not sure if they did it properly, but 200 seemed to be the result. So we're going to use 200 kPa or kilonewtons per, what you call it, per square meter. That's what you use. So this is allowable bearing pressure. And what you then do is it automatically calculates for you. So this is the load, that is the total unaffected load, divided by 200. This is the area, and then assuming a square base, all they're saying is you're going to need to use either 1.34 by 1.34. So in this case, 1.4 by 1.4 or 1.35 by 1.35 would work. So basically, this is the process that we'll be going through as you're designing or you're calculating the preliminary size in your loads. And in this case, a base will work because this is not too large. But in a case where we needed to use a base that's 2 meters, 2 point something by something, that means you definitely need to change from maybe a base to piles, or you need to change to a raft footing, because already 2 meters is too much. You're using a lot of material, so you need to be innovative. Piles might be more cost effective and much better for your building. But in this case, 1.4 is still okay, so we're definitely going to stick to pad footings. So what we're going to do in the next video, there is going to be part 6. What we're going to do is we're going to do a quick rundown of I think we still have 2 columns or 3 types of columns. We have C2, C3, and C4. We're just going to do a quick rundown now that you know most of the nitty-gritties of this. And remember, as I was telling you, I was giving you the more appropriate thing that you would want to do given your circumstances. And remember, selection of the load factors, the live load factors, and also whether you want to average your slabs or to average your beams is solely dependent on you as the designer. If you want to be more conservative, just do what I did, I average. But if you want to be more accurate and more precise, do everything for each section on its own. What you would do is you calculate for the canopy slab on its own, then you do for your actual slab on its own. Then for the beams, you actually do it for every single beam. You calculate the load that is redistributed to your column on its own. In our case, I just decided to average out because we're doing a quick tutorial which we want to be finished in 30 minutes. So this is basically what you would do. But then one thing that I need to tell you, when we are now doing the design from the top going to the bottom, that needs us to be more accurate. So we're going to be spending our time on there, and we will not be talking a lot. We will actually be doing it straight to the point. And I might actually just try and do the mathematics 10 minutes before. The mathematics, what I mean is just do the data calculation that we need to see the input that we need, and we key it straight into the Excel before the tutorial, so that next time we just flow through the tutorial. But this is part 5 of Let's Design. If this is your first time, subscribe to the channel, like the video, share the video. Everything you want is in the link in the description below. And I will see you in part 6, and let's just finish this. So in part 6, if we're done with this, that means we need to do a walkthrough just to summarize everything that we've done from part 1 to part 6, because remember, my Prokon is still in demo. They have not yet renewed the license. So whilst we wait for the license, we do a walkthrough and we see what else we can do when it comes to Prokon, structural, and anything else that you need on this channel, even detailing. So without wasting too much time, please subscribe to the channel, share the videos, and I'll see you in the next video.